Okay, so I am set and ready to go through the second part of this section 5.4. So we're going to look at what we call the net change theorem. At least that's what our textbook calls it. I think of this as the fundamental theorem of calculus. So we're mainly going to be looking at these two equations right here. And this right here is mostly what we're going to be looking at, which is really the fundamental theorem of calculus. All right, so, and it is a change. It is a net change, and I'll explain what's meant by that as I go through an example here. So this is the fundamental theorem of calculus, which essentially tells you how to evaluate a definite integral, which ultimately finds an area under a curve. If you look at this form right here, if you subtracted or just moved this f of a the other side, well, what you would get is you would get the fundamental theorem, which is usually the second part of the fundamental theorem. F of b, f of a equals the integral from a to b of f prime x dx. Okay, so that's your fundamental theorem. They're just written in the same form, so that's the same equation. One of them is though solve for f of b. Okay, so what I'm going to do on this, I'm going to use a graph and an applet that I found on the internet to explain geometrically really what this is doing. Okay, so I'm going to try to show how this goes like this. So I'm going to go ahead and show you how to do this integral, and then we'll kind of look at the geometry behind this, because I want you to really understand why you're doing that f of b minus f of a. So the way that you do this integral is, first of all, what you do is you do the antiderivative. Now I picked a real simple example. You can do the antiderivative in your head by the power rule. You add 1 to the exponent, divide by the result. This now is what we would call the antiderivative. We usually label with capital F, and then we're going to evaluate that from 2 to 5. So I want to show you what this does in a geometric sense here. So the idea is we just plug in, we just plug in the 5. We're really finding f of 5. So that's just 5 to the second over 2. And then what we do is we plug in the 2, which gives you the antiderivative evaluated at 2, which would now just be 2 squared over 2. Then you subtract the result. So what you would get is this would be 25 over 2 minus 4 over 2. So just using a decimal, that's 12.5 minus 2. So you get that net change of 10.5. Okay? Now what I'm going to do is I'm going to open up this applet, and I've just kind of copied these graphs because I want to show you the main connection that's going on here then. So what we just did is we did the integral from 2 to 5. And when we did the integral from 2 to 5, right here, we got 10.5. Okay, so I got the same thing there like that. Well, what the fundamental theorem of calculus is really doing, this f of 5, that capital F of 5, all that's doing is the area from 0 to 5, which is 12.5. Okay, the f of 2, if you do the f of 2, then you're just doing the area from 0 to 2, and that area from 0 to 2 is 2. So you're doing this big area, 5, and then you're doing that small area, and that gives you this leftover area like that. Okay, so I'm going to go back to my OneNote here, and I want to show you just in this diagram what's really going on this. So really what's happening is this area right here is equal to 10.5. Okay, this area here, well, that's what the 12.5 is. Okay, so that area is 12.5. Okay, and then this area here, well, that's the 2. So what you're really doing in a sense here is you're doing a net change. You can think of it like this. So really what's happening is if you take the big area here minus the small area here, then you end up getting the leftover area like that. It's just the big area minus the smaller area gives you that leftover area. So in a sense, what's going on is that f of 5, well, that's given this big area all the way from 0 to 5. That's given 12.5. the f of 2 that you evaluate, that's given the small area from 0 to 2. You subtract the result, and you get that leftover area. So just think of it as the whole. I like to think of it like this. The part is equal to the whole minus the other part, like that. Okay, actually I should say it like this, okay? All right, so if you do the whole minus the part, you get the rest is left over. Okay, so that's the idea. So I hope that makes sense to you. That's what's meant by the net change theorem, which is the fundamental theorem of integral calculus. Okay, so that's a good way to look at that idea. Okay, so what we're going to really do in this section on the net change theorem mostly is we're just going to go through and calculate some definite integrals on here. So I'm going to zoom on this a little bit, and then we'll start getting going on this. And all these things can be checked pretty easily with a graphing calculator. Okay, I'm a little trouble zooming in on stuff today. Okay, there we go. Okay, so let's go ahead and do this. So this is a definite integral. The first thing we do is we find the antiderivative. And when we find the antiderivative, we usually represent that by capital F. Okay, so you can do this antiderivative in your head. Technically, if you want to, we're just doing the integral of sine x dx, and then you're doing 2 times the integral of cosine x dx. I'm just going to get the antiderivative, and then in the second step, we'll go through and do the evaluation. Okay, everything's going in reverse. So the integral of sine x is negative cosine x. Okay, whoops, need the x there. Then we bring down the 2. The integral or antiderivative of cosine is sine x. Now you don't put a plus c because this is a definite integral. So again, what we're doing on that, and you don't have to do this every time you do the problem, but if I take the derivative of the antiderivative, let me show you what would happen. So our antiderivative is this. If I take the derivative of negative cosine, that would be negative, and remember the derivative of a cosine is negative sine, and then if I do the derivative of sine x, that's cosine x. So notice you just get what we left over where we began at sine x minus 2 cosine x. So if you get an antiderivative, if you take the derivative of it, it should get you back to the beginning. So the second major thing that we do on this is now we evaluate. So this is where we do the, and that shouldn't be a prime. Usually the antiderivative is just capital F, and then we're going to do the upper limit pi, and then minus the lower limit 0. Okay? So what we generally do on this is generally you'll see me writing a 0 to pi like that, and then in step 2 when I do this I just do negative cosine of pi minus 2 times sine of pi. That's going to be the f of pi part. That's giving a big area. Then subtract off, and then you do negative cosine of 0 minus 2 sine of 0 like that. Okay? Now, so that is really the f of 0 part like that then. Well, all this stuff can be looked at on a unit circle. If you're at 0, we have the point 1, 0. If you're at pi, we have the point negative 1, 0. So basically, when we're doing the cosine, that's the x value. So we'd have this. The cosine of pi is negative 1. So that would give us negative 1 minus 2 times the sine of pi. The sine of pi is the y value, so that's 0. Then we move over here. The cosine of 0 is 1, so that's negative 1. That negative was already there in the antiderivative. And then the sine of 0 is the y value, so that's that. So from here, you're just doing evaluation and doing arithmetic. So this looks like 1 minus 0 minus negative 1 minus 0. So that's 1 minus negative 1. So 1 plus 1 is equal to 2. Okay, so that is the area under the curve of this function then. Okay. Now as I do some of these problems, not all of them, some of them we're going to check on the calculator. So I'm going to pause here for a second and get my calculator set up, and we're going to check. Okay, so let me show you how you graph this and kind of what the geometric interpretation of this thing would be then. Okay, so as we're doing this, let me pull up my calculator real quick here. So what I'm going to do is just put in the function. So we go back to the original function, sine x minus 2 cosine x. We're going to graph that. We're interested in 0 to pi. Now on the window, this is real important. If you put pi there, there's a chance that you might get an error when you look at this area under the curve. So I always recommend the limits, try to go a little bit beyond it. So if pi is 3.14, let's go to 4. And the 0 is probably okay, but let's go to -1, okay, just for that reason. Scale by 1, and then let's do y from -4 to 4, like that. So you want to get your window set up. Now we're going to graph this function. You also want to make sure that you're in radian mode if you're graphing this, so we're good there. So let's graph it. So what we're actually doing is finding the area under the curve from 0 to pi, which is over here. So you have some negative area there, you have some area above the x-axis, so you're going to have a net change or a net area in there when you subtract those two. So again, what you do is you go second calc. Option 7 allows you to do an integral. The lower limit is 0 in our integral, so I type that in. The upper limit is pi, so I go pi. And I press enter. I think this is so satisfying to watch this. It's going to shade that. And then right there, see, the integral is 2. So that's the exact value you got. And realistically, what we did when we did the antiderivative at pi, the antiderivative at pi was evaluate pi was this whole entire area right here. Okay, then if you do the antiderivative at 0, that's 0. Okay, so you end up getting that worked out like that. So that would end up giving your net area like that. Okay, so you can always check your calculator and work that out like that then. Okay, so check it out and see if you get it right. Okay, I won't do that on every problem, but I'll do it on several of the problems. Okay, all right, let's go to this one and work out the antiderivative on this one and use the fundamental theorem to get the area under the curve. Okay, so the first thing on here is when we do the antiderivative, we're just doing the antiderivative of x and the antiderivative of cosine 2x dx. Okay, so we're really finding the antiderivative. One thing that's real useful, earlier in this section, there was sort of a series of formulas that are real important to learn, and I'm just going to refer back to there real quick. So if you're doing the integral of cosine ax, which is what we're doing, then it's 1 over a sine ax plus c is what that antiderivative is. So you want to be sure that you get these formulas down real well when you learn this stuff then. So I'm just going to paste that over at the side, and then we'll refer to that formula here, okay? But you want to get this memorized so you don't have to spend a lot of time looking formulas up. So anyway, the antiderivative goes like this. This one would be power rule, so that's x squared over 2. And then this one, okay, a is really 2 in here, so you would have 1 over 2 sine of 2x, okay? Now we're not going to put the plus c on that. Since we're doing a definite integral, we're going to evaluate that from negative pi over 2 to pi over 2. So that's step one, is just simply getting that antiderivative. Then we're evaluating the antiderivative at the upper limit, okay? And that's really given the area from 0 to pi over 2, okay? Then what we're going to do is subtract evaluate the antiderivative of negative pi over 2 like that. Okay, and this will probably, these numbers go to the unit circle. Okay, so when we do that, just plug in the upper limit. So the upper limit, it looks like you would have pi over 2 squared all over 2, and then you would have plus 1/2, and then you would have the sine of 2 times pi over 2, like that. So what I'm doing on that is I'm just plugging in that value into the x of our antiderivative, like that, okay? Then what we do is we do the f of negative pi over 2 the same way, so this would just be negative pi over 2 squared over 2 plus 1/2, and this would be sine of 2 times negative pi over 2, like that. And then we subtract the difference like that. So that's the fundamental theorem of calculus. So we need to work this out and see what we get. Okay, so if we square this, that would be pi over 4. And then you're really dividing by 2. And we'll work that out in the next step. And then this is 1/2 sine of pi, because the 2's cross out. Okay, then when we go over here, if we square this, that would give positive pi. Whoops, I made a mistake here. This would be pi squared over 4. And this right here would also be pi squared over 4. Again, we're dividing by 2, or you can just think of that as multiplying by 1/2. Then over here we would have plus 1/2 sine. 2's cross out. Then we have negative pi like that. Okay, so we've got a couple of things to do on the unit circle and kind of polish this up a little bit. So this part that says pi squared over 4 divided by 2, well, that's really just pi squared over 4 times 1/2. So that's pi squared over 8. Okay, so we're going to write that down. That becomes pi squared over 8. Then we have 1/2 sine of pi. So again, on a unit circle, if you're at pi, you're at the point -1, 0. So the sine of pi is going to be 0. So this whole thing right there becomes 0. It's always nice if 0 pops up. Okay, and then this part right here, we already did that. That again is pi squared over 8. Then we have plus 1/2. And then negative pi. Of course, negative pi is just clockwise, 180 degrees. So that's also 0. Okay, so it looks like what we're going to have now is pi squared over 8 plus 0 minus pi squared over 8 plus 0. So it's kind of interesting. It looks like we're going to get 0 on this, so it's probably worth looking at the graphing calculator on this to interpret this. So we just have pi squared over 8 minus pi squared over 8. So that net change is going to be 0. So that looks like that's what the answer to that integral is then. Okay? The hardest part a lot of times in doing the fundamental theorem of calculus is if the antiderivative is simple. This part right here, you can get into some pretty hairy arithmetic sometimes, okay? So it's real easy to make mistakes on this if you're not being really careful with what you're doing. So what I'm going to do on this problem then is we're just going to check this on the graphing calculator. So I'm going to put in x plus cosine of 2x. And again, we're going to set up a viewing window from negative pi over 2 to 2. Now, I would not do negative pi over 2. I would expand a little bit and go beyond that. So why don't we just go negative pi to pi, and then that way we're a little larger than those limits are there. So let's just go negative pi to pi. We can scale by 1. It doesn't make a bit of difference what you scale by. And then we'll just use this y window and see if this looks okay. So I'm going to graph this. That's an interesting looking graph. I like that graph. Okay, so let's go ahead and let's just check this like I showed you on the previous example. So again, we go second trace, option 7. The lower limit is negative pi over 2. Okay, the upper limit is pi over 2. Now it'll shade it in. Let's see what the calculator gives. Okay, it's not giving 0, but that number right there is in scientific notation. So if you look at that number that's coming out on the calculator, well, actually what that is it says negative 4.08 times 10 to the negative 14. All that means is this decimal gets moved back 14 places, so it would be like 0, 0, 0, 0, 0, 0. So for all intensive practical purposes, that's 0. Okay, the calculator didn't do what I did. It didn't do it numerically by hand. It did it with some kind of a computer program, maybe utilizing a trapezoid rule or something called Simpson's rule. So it does it numerically, so it's not going to necessarily be perfect. So it looks like that checks out then. And notice on this, what would happen is this area above the curve is the same as this area below the curve. So they cancel each other out. So that's what happens. It's hard to see that perfectly, but that's what happened. Okay? All right, so that'll take care of that. Now let's go ahead and let's look at, I'm going to let you pause and do these examples, then I'll be posting this video. Okay? Work these out, resume, and see if you're doing these correctly. Okay, so I'll let you go ahead and check and see if you did these right. These didn't work out too bad. So what I got on the first one was either of these two answers. 1/2 e to the 2 pi minus a half, or you could factor the half out and get 1/2 e to the 2 pi minus 1 as the exact area under the curve. Second one just turned out nice and sweet and got 1. Okay, so I'll just go over a couple of things. A couple of things that did show up on this, and that will show up in this section, is these basic formulas, these antiderivative formulas. So the integral of e to the at is 1 over a e to the at. So this part right here, you want to check that you got your antiderivative right, 1/2 e to the 2t, and then the antiderivative of cosine is sine t. So you have your antiderivative, then plug in the upper limit to get 1/2 e to the 2 pi minus sine pi. Plug in the lower limit to get 1/2 e to the 2 times 0 minus sine 0. Sine 0 is 0. Okay, so you end up having 1/2 e to the 2 pi. Right here, e to the 0 is 1. So if you look over that, that's what you'd end up getting on that problem. Okay, right? Next one, the antiderivative of secant squared is tangent, but the antiderivative of secant squared ax is 1 over a tan ax. Okay, so we got that. So here's your antiderivative, 1 over 2 tan of 2x, evaluated from pi over 8, negative pi over 8 to pi over 8. So again, I plug in. Now what I did, and you don't have to do this, I mean, if you have a constant, I just put that out of the whole computation. So I just put down the half, and then I did tan of 2 times pi over 8 minus tan of 2 times negative pi over 8. Okay, this reduces to pi over 4 and negative pi over 4. And then on the unit circle at pi over 4, you're at the point root 2 over 2, root 2 over 2. Remember, the tangent's y over x. So if you take root 2 over 2 divided by itself, you get 1. And negative pi over 4 is at this point on the unit circle. So if you do y over x there, you get negative root 2 over positive root 2 over 2, so you get negative 1. Okay, so notice I get 1 minus negative 1, so you're really doing half of 2, so you get 1. Okay, so hopefully that worked out for you okay. So this will be the second part of the video, and then the third part will be a few physics examples. Okay, good luck.